Having covered the matrix vector multiplication, now we can move to matrix-matrix multiplication. In matrix-matrix multiplication, a matrix can take another matrix as input, as opposed to taking a vector as we discussed matrix vector multiplication. So when we are multiplying a matrix with another matrix, we have this formula up there. So notice the capital letters. We have AX equals Y. In this example, both X and Y are matrices. So our operating matrix, the A matrix, takes another matrix Y, X, and that gives you another matrix Y. So when we are doing the matrix-matrix multiplication, it is very similar to matrix vector multiplication, but on steroids. So I promised you, if you had an understanding of inner product, it's quite easy to understand what matrix vector multiplication is, because we discussed every row of the matrix A gets inner producted with the input vector, right? So it was a matrix vector multiplication. Guess what? In matrix-matrix multiplication, it's the same logic. So every row gets multiplied with every column of gets inner producted with every column of the second matrix. So therefore we will have to have some dimension mismatch, dimension matching rule, and we will have to avoid some dimension mismatch, just like we were careful in matrix vector multiplication. And that's something when you're building neural networks, if you're not careful about what tensors are coming and how they are getting multiplied with the layers, because you will see that the layers are going to be your matrix A, except they're not going to be called A, they're going to be called W for some reason that we will cover, probably in machine learning courses, maybe in following weeks of this course too. And your input is typically called X. So when we multiply the matrix-matrix multiplication, we will have a similar dimension rule. So we will have M rows in the first matrix and n columns, and the number of columns will have to match the number of rows in the second matrix, because the number of rows in the second matrix is the dimensionality of its columns. So when we actually conduct matrix-matrix multiplication, as I mentioned, we take every single row of the first matrix and multiply it with every single column of the second matrix. Let's take the first row of the first matrix and first column of the second matrix. There you go. You get yourselves a very simple inner product, right? So I know how to calculate inner product. I go through every single element of both vectors, right? Where do I put this inner product? The row index that you take from matrix A and the column index that you take from matrix X tells you where you're going to put this number, which is the result of the inner product in the matrix Y. So when you multiply each and every one of rows, say the second row also goes from matrix A, first column comes from matrix X, you're going to put it there. So let's pause and understand some of the things. One, in order for you to be able to do the inner product, as we discussed when things were simple, still simple, the dimensions of the two vectors should match, right? Therefore, you get yourself a rule. The number of columns of the first matrix, which is going to represent your horizontal pen or vectors, row vectors, and every column of the second matrix, which are going to be your vertically located pens or column vectors. They have to match the dimensionality And this inner product, in order for this inner product to happen, the number of rows in matrix A have to match the number of columns. The number of columns in matrix A have to match the number of rows in matrix X. So this inside indices N must match N. Another thing, since we are covering all of the rows of the matrix A and going ahead and putting it on the corresponding row of the output, there you go. You know the number of rows in the resulting matrix. The number of rows in the resulting matrix is the same as the number of rows in A. And similarly, since we're iterating over each and every one of the columns of the matrix X, there you go, you know the number of columns in the resulting matrix Y. So the resulting matrix of the matrix multiplication of M by N matrix by N by K matrix results in a M by K matrix. So let's simplify things a little bit. Since we just learned matrix vector multiplication, let's see this matrix A as a matrix that's there, sitting there, and it takes every column of the matrix X one by one, resulting a column vector. So that's actually what happens. Now I would like you to see the matrix A as some matrix that is going to represent a function, an operation that's to be learned or to be functional in a neural network or in a system, and every column of the matrix X to be a data point. So you can actually stack the data points in that dimension, and matrix A can be in parallel applied to every column of the matrix X. So when you multiply A by the first column of matrix X, you get the first column, first output of matrix Y. And when you multiply the same matrix with every single column, any column of matrix X, you get that column of matrix Y. So this is important because when we are doing matrix multiplications in digital hardware or GPU or somewhere, you do not want to keep moving data from your memory to your processors. When you move your A matrix to your processor, you know that the same A matrix is going to do the same job for each and every one of the columns. So that's going to be a little bit important when you go to AI engineering parts of the things. One other thing that I would like to mention, since I discussed how these things need to sit next to each other and how the columns should match, how the rows should match, and etc. One thing that could be misinterpreted by looking at this X equals Y, very naive looking equation, and thinking it's very similar to the scalar multiplication that we learned in, middle school, elementary school. You might think that A times B, I shouldn't call it times, AB should be BA, but I must warn you that you see that AB is not equal to BA. Now let's go ahead and see one example of this matrix multiplication in action. So we have a 2x2 matrix A and 2x2 matrix B. We see the inner dimensions match. So we're going to take the first row of the matrix A, and with the first column of the matrix B, we get our inner product 0 and put it there. And do the same thing for the second column. Second row, first column, it goes to the second row, first column of the resulting matrix, and it goes, the second row, second column goes to the resulting point of the resulting matrix. So, my dear friends, this was MATML for you, and that's the core. You just learned the key operation in deep learning: linear layer matrix forward or layer forward, backward, extension. So there are all these matmul operations interlinked with some nonlinearities.